Welcome back to BE 110. We'll continue our discussion of the constitutive equation by examining the equations for a linearly elastic or Hookean solid. Elastic solids have the following characteristics. First, they should have a unique unloaded natural state to which they return when all the stresses are removed. And the stress depends only on the strain in the material. More generally, as a result of this, we can say that elastic solids store all the work that's done by the stresses in deforming them as potential energy, or sometimes we call it strain energy. And this energy is released when the stresses are removed. Thus, the deformation of an elastic solid is a thermodynamically reversible process. And we can conclude from this that the stress in an elastic solid is independent of the path or history of the strain. In other words, it doesn't matter how the strain state was achieved, only what the strain state is, that's the only determinant of the stress in the elastic material. And the process of loading and unloading a material is reversible so that all the work done on the material is stored in it, and then it's all released when the material is unloaded. Elasticity is very useful idealization. For many materials, especially engineering materials, the strains that they experience under normal design or working conditions is very low, and so under these lows the stress-strain relationship is linear, and we can use the Cauchy infinitesimal strain. Imagine we have a specimen subjected to uniaxial tension or compression with a cross-sectional area A, so that the uniaxial tensile or compressive stress, sigma xx, is F over A. And the length is L, and so the strain is delta L divided by L. If we plot the stress versus strain in a linearly elastic solid, we get a straight line for tension and compression within a certain range, and the slope of that straight line is called the Young's modulus, and it's a measure of the elastic stiffness of the material. At some point, if we stretch the material beyond a certain point, the material becomes anelastic. This is called the elastic limit, and in the case of a ductile material, the elastic limit would be the yield point at which the material becomes plastic and starts to form irreversibly, such that when we unload it, it doesn't return to its original length. In a brittle material, the elastic limit may correspond with the point at which the material starts to fracture and fail. Another experiment that can be done in a linearly elastic material is to measure the ratio of the transverse strain components, for example EZZ or EYY in this direction, in proportion to strain in the longitudinal or loaded direction, in this case EXX. In a linearly elastic material, and we see this in many engineering materials for small strains, the strain in the transverse direction is linearly proportional to the strain in the longitudinal direction. It's of the opposite sign, so if we're stretching the sample in this direction, then it'll shrink in the other direction, and that ratio of the negative shrinkage strain to the positive tensile strain is called the Poisson ratio, and is typically about 0.3 or 0.4 in many engineering materials. These two technical constants, E, the Young's modulus, and nu, the Poisson ratio, can both be measured at the same time in a single uniaxial tension test. And if the material is isotropic, meaning that had we done that same test from a sample of the material cut from any other orientation, we would have got the same result, then in fact these two constants, the Young's modulus and the Poisson ratio, turn out to be sufficient to completely define the properties of an isotropic Hookean elastic solid. Now, it's important to realize, as we've pointed out before, that the context of the of the loading, not just the material itself, determine the accuracy of the assumption of linear elasticity. You can see that in linearly elastic materials, this approximation holds well, but for small strains, typically considerably less than 1%. Beyond those small strains, we reach the elastic limit, and not only is the stress-strain behavior not linear, it also quickly becomes non-elastic. So neither the assumption of linearity or elasticity will be valid above a certain loading. So with that background, let's derive Hooke's law for a continuum. In a linearly elastic Hookean solid, the stress is linearly proportional to the Cauchy infinitesimal strain. So we can write that the components of the stress tensor Tij equals Cijkl times epsilon kl, where Cijkl are the components of the fourth order tensor of elastic constants. Just as we reasoned for the linear viscous fluid, this tensor has a total of 3 to the 4 or 81 components. However, because of the symmetry of the stress Tij and the strain epsilon kl, the number of independent constants would reduce from 81 to 36, which I think of as the number of constants in a 6x6 matrix relating the 6 independent components of the stress tensor to the 6 independent components of the strain tensor. However, we can actually do better than that. If you recall from conservation of energy that the rate of work done by the stresses was given by the product Tij dEij, or the trace of the product of the stress tensor with the rate of deformation tensor. Now recall that the rate of deformation tensor dEij is also the strain rate, or epsilon ij dot, or d epsilon ij dt. So from this we can write dw dt equals Tij d epsilon ij, or dw equals Tij d epsilon ij. And now we can integrate this, substitute Cijkl times epsilon kl for Tij, integrate with respect to epsilon ij, and we'll get 1/2 Cijkl epsilon ij epsilon kl. Now if we see that this expression would be same if we switched the order of epsilon ij here and epsilon kl here, which means that we should be able to switch the order of ij here and kl here in this expression. And that leads us to the conclusion that Cijkl equals CKLij. So this additional symmetry further reduces the number of independent constants from 36 to 21. So you can think again of that 6x6 matrix relating the 6 independent components of the stress to the 6 independent components of the strain, but now that's actually a symmetric matrix. So this reasoning is also true for the viscosity tensor Bijkl that we derived for linear viscous fluids. But as with Newtonian viscous fluids, to simplify any further, we need to consider the material symmetry. Unlike fluids, many material symmetries are possible in solids. It's easy to imagine and think of solids that have different properties in different directions. Like muscle has different properties along its fiber orientations, so do tendons and ligaments and other fibrous connective tissues. The simplest material symmetry is isotropy. So just as we did before for the Newtonian viscous fluid, we can write down a general form for an isotropic fourth order tensor, one that also satisfies the symmetry conditions that we just derived based on the symmetry of the stress and the strain and on the conservation of energy. So as we saw for the linear viscous fluid, we also see that the general isotropic expression has two material constants, lambda and mu. So we getCijkl equals lambda times delta Ij delta Kl plus mu times delta Ik delta Jl plus delta Il delta Jk. Now substituting this into our linear expression for the stress-strain relation, we get Tij equalsCijkl times epsilon Kl is equal to lambda times delta Ij delta Kl epsilon Kl plus mu times delta Ik delta Jl times epsilon Kl plus mu times delta Il delta Jk epsilon Kl. And now we can see that these expressions simplify, so we get Tij equals lambda times delta Ij, and delta Kl epsilon Kl is epsilon Kk. This Kl turns this L into a K. Delta Ik delta Jl times epsilon Kl becomes epsilon Ij. K becomes an I, L becomes a J. And similarly, delta Il delta Jk times epsilon Kl becomes an epsilon Ji. Since epsilon Ij equals epsilon Ji, because it's symmetric, we get lambda delta Ij epsilon Kk plus 2 mu Eij. Or writing this in direct notation, the stress in an isotropic Hookean elastic solid is lambda times the trace of E times I, the identity tensor, plus 2 mu times epsilon. So this is Hooke's law for an isotropic elastic solid. Lambda and mu are elastic moduli that are known as the Lamé constants. Since strain is dimensionless, they have the same units as stress has. We can find the Lamé constants in terms of technical constants such as the Young's modulus and Poisson ratio, and we'll do that next time. Writing the constitutive law out now in full, for the isotropic Hookean elastic solid, we get the following. T11 is equal to lambda times epsilon 11 plus epsilon 22 plus epsilon 33. So that's the trace of E. T22 equals lambda times epsilon 11 plus epsilon 22 plus epsilon 33 plus 2 mu epsilon 22. And T33 equals lambda times epsilon 11 plus epsilon 22 plus epsilon 33 plus 2 mu times epsilon 33. And then the shear stress components, T23 is 2 mu times epsilon 23, T13 is 2 mu times epsilon 13, and T12 is 2 mu times epsilon 12. So you can see here that the modulus mu directly relates the shear stress to the shear strain. It's known as the shear modulus and often denoted by G, which is another technical constant. Let's try an exercise now. Try to simplify the constitutive equation for a Hookean isotropic elastic solid to obtain an expression for the Young's modulus capital E in terms of the Lamé constants lambda and mu and the Poisson ratio nu. Did you get A, that E equals 2 mu, B equals lambda minus 2 mu lambda, C equals lambda minus 2 nu lambda plus 2 mu, D equals lambda minus 2 nu lambda, or E equals lambda plus 2 mu. So let's start by writing an equation for the special case of uniaxial tension, which would be T11 equals E times epsilon 1 by definition of E, which from the constitutive equation for the Hookean elastic solid will be lambda times E11 plus E22 plus E33 plus 2 mu times E11. Now, making use of the definition of the Poisson ratio, namely that E22 and E33 in this case is equal to minus nu times E11, then we get that E times epsilon 11 is lambda times epsilon 11 times 1 minus 2 nu plus 2 mu times epsilon 11. Now we can cancel epsilon 11 on both sides and get that E is equal to lambda times 1 minus 2 nu plus 2 mu, or lambda minus 2 nu lambda plus 2 mu, which is answer C. Now let's consider the other stress components in this problem and use them to eliminate nu from the previous answer to obtain an expression for the Young's modulus E only in terms of the Lamé constants, lambda and mu. Did you get A, mu times 2 lambda plus 3 mu all over lambda plus mu? B, mu times 3 lambda plus 2 mu over lambda plus mu. C, lambda squared over lambda plus mu plus 2 mu. D, 3 lambda plus 2 mu over mu times lambda plus mu. Or E, mu times 3 lambda plus mu over lambda minus mu. So now we make use of the fact that the normal stresses perpendicular to the axis of the tension, T22 and T33, are equal to 0, which gives us from the isotropic Hookean elastic solids constitutive law that lambda times epsilon 11 plus epsilon 22 plus epsilon 33 plus 2 mu times epsilon 22 or epsilon 33 is equal to 0. Now substituting in for epsilon 22 and 33 again using the Poisson ratio, we get that lambda epsilon 11 times 1 minus 2 nu minus 2 mu nu times epsilon 1 is equal to 0. And then again we can cancel epsilon 11 from this to get that lambda plus 2 lambda nu minus 2 mu nu is equal to 0, which we can rearrange for nu terms of the Lamé coefficients equals lambda over 2 times lambda plus mu. Now we can substitute that into the expression that we got above for E, which was lambda minus 2 nu lambda plus 2 mu, to get lambda minus 2 lambda times nu, which is lambda over 2 times lambda plus mu, plus 2 times nu. Then that can be rearranged to lambda times lambda plus mu minus lambda squared plus 2 mu times lambda plus mu all over lambda plus mu. We cancelled the 2's here, multiplied this term and this term by lambda plus mu. The lambda squareds here cancel, so we get lambda squared plus lambda mu minus lambda squared plus 2 lambda mu plus 2 mu squared over lambda plus mu. These terms cancel and simplifies to mu times 3 lambda plus 2 mu divided by lambda plus mu, which is answer B.